Very good. But if you want, you can have your one piece
I
right now or later.
I just had a bunch of spoonable food.
No worries. But yeah, it's gonna be one per person because there is only a few. I want to make sure it goes around so double team.
Are they all different?
Yeah, they're all different.
Morrison Planetarium's live stream of Tour of the Universe. My name is Ryan White. I'm the Senior Director of Morrison Planetarium and Science Visualization here at the California Academy of Sciences, and I'll be your host for the next half hour as we travel from Earth out to the edge of the observable universe, a program that we do every Wednesday as a live stream at this time, 4:30 p.m. Pacific. And yeah, this is a little bit different because for the next several weeks, we're actually going to be delivering this as a presented program, I'm coming to you from kind of deep in the bowels of the Academy, underground, underneath the planetarium, actually. Typically, we simulcast this program from Morrison Planetarium, so you're seeing the same show that our audiences are seeing in the dome. But for the next few weeks, I and a few other presenters will be giving a live tour of the universe that you can interact with a little bit more. So if a question comes up during the course of the program, feel free to put it in chat, and if we have time, we can put those up, share that with the live stream, and answer questions that you happen to have. But for right now, you actually don't need to see me for any of this program, so I'm going to focus on our software. This is an open source software called OpenSpace, and we'll take off from our International Space Station and fly out into space. So I'll disappear for now, and we'll start our program here at the International Space Station. This is a great place to start because this is as far as humans travel out into space these days. A few hundred kilometers above Earth's surface. Astronauts are hard at work in the International Space Station, and you can kind of imagine being in this place. The sort of living quarters are human scaled, and the entire International Space Station is maybe about the size of a football field from one end to the other. And since soccer fields and American football fields are about the same size, it doesn't matter whether you interpret that as American football or as football. But we'll use this as a starting point and go much, much farther out into the universe, because a lot of what we understand about the universe around us actually comes from observations that are made by telescopes, both on Earth and in space, and we have put together a three-dimensional model of the universe, placing these objects in their correct relative locations compared to Earth, and that allows us to take a virtual voyage through the universe much, much farther and faster than our rockets can take us out into space. So even though astronauts only travel this far, a few hundred kilometers above Earth, we're going to travel much, much farther. I added the orbit line for the International Space Station. That's its trajectory around Earth. And if you're a keen-eyed observer, you might have noticed that our cloud image is a little pixelated here, and in fact there's a kind of giant seam running through the ocean. That's because we're actually putting data from yesterday up on Earth's surface, and in fact you can see the limits of the satellite here, because these mapped images don't extend all the way to Earth's North Pole. So we're actually seeing weather patterns out in the Pacific Ocean as they existed yesterday, and again the trajectory of the International Space Station around Earth, sort of encircling Earth. And this is just another way in which we incorporate real data into our three-dimensional model of the universe. Now, we're rapidly leaving Earth behind, and what I'd like to do now is to bring up a few more diagrammatic elements. In this case, the orbits not of any man-made or human-made objects, but rather the orbits of the planets, and also the orbit of Earth's moon. So if you look out kind of toward the edge of the screen here, you'll see this orbit encircling Earth. That is the orbit of our moon. Now, the moon is another important place in terms of human exploration of space, because that's the farthest any humans have traveled out into space. Back in the 60s and 70s, 12 lucky Americans got to make the trip, and of course we're now planning with the Artemis mission and with other international missions for humans to go back to the moon. But for purposes of this discussion and this tour of the universe, what I want to emphasize is that's as far as humans have traveled out into space ever. And yet we're going to travel much, much farther during the course of the next half hour. And we do that, again, by compiling observations and data from multiple telescopes, multiple missions, to be able to create this coherent three-dimensional model of the universe. The lines you see in the background are the orbits of some of the other planets, but before I leave our Earth-Moon system behind, I just want to point out one thing. This is, again, as far as humans have traveled out into space, the distance from Earth to the moon. It's a distance of about 400,000 kilometers, or if you prefer the units that Americans seem to prefer, you might want to call that 240,000 miles. And if you think about it, maybe that's as far. If you had a car for a really long time and you drove it all the time, you might drive it a total of 250,000 miles, or 250,000 miles, 240,000 miles. It's a lot of miles on the odometer, but maybe you can imagine how long it would take to make that journey. That's the distance between Earth and the moon. Now, astronauts made that journey in just a few days back in the 60s and 70s, but I want to introduce one other way of measuring distance, and that is using light travel time. Light travels at the same speed through the vacuum of space, 186,000 miles per second, or 300,000 kilometers per second. So if you think about that, it's about a second and a half of light travel time from Earth to the moon. So when you look at the beautiful full moon in the sky, you're seeing it as it was a second and a half ago. And as we pull a little farther back, we can use this same measurement tool, the speed of light, and what we call, in this case, we could call that second and a half 1.5 light seconds. And then if we pull back even farther, we can take a look at, again, the orbits of the other planets kind of coming into frame in the upper left-hand side of our image. And then the sun at the center of our solar system. And if you want to think about the distance between Earth and the sun, that distance is around 150 million kilometers, 93 million miles. And that distance is traversed by light in about 8.5 minutes. So we can call that distance 8.5 light minutes. Now, if you think about that distance from Earth to the moon, a second and a half, that's kind of like a brief pause in conversation. The distance from the sun to Earth, maybe it's a little bit more like a quick lunch. If you really hurried, you could maybe wolf down a lunch in less than 10 minutes. The distance, the time that light takes to travel from the sun to Earth. But now, as we pull even farther away, so the orbits of Mercury, Venus, Earth, and Mars in the center of the frame, Jupiter, Saturn, and then Uranus, and finally Neptune's orbits all kind of coming into frame. Now we're seeing our entire solar system, at least the orbits of the planets in our solar system. There's a lot of other stuff in our solar system, and unfortunately we won't be visiting many of those places today. Instead, I just want to use our scale of the solar system as yet another kind of benchmark in terms of size. And the distance across Neptune's orbit from one side to the other is a little less than 8 light hours. So if you want to think of that, that's maybe a good night's sleep. So, distance from Earth to the moon in terms of light travel time, second and a half pause in conversation, 8.5 minutes from Earth to the sun, something a little bit more like a quick lunch. The distance across our solar system, 8 light hours, a good night's sleep. And yet, the distance to the nearest star is about 4 light years. That's a high school or college education. So, the distances become mind-boggling pretty quickly when you try to compare the distances inside our solar system even to the nearest stars, and we're going to be going much, much farther out into space. But before we do, I do want to point out one other thing. At this distance, as we're looking at our entire solar system, as I mentioned, we have plenty of other objects in our solar system, asteroids, comets, but the planets that whose orbits I'm showing, we have, of course, visited, and some of our spacecraft, I should note, astronauts haven't visited, but our spacecraft have. And some of the spacecraft have done flyby missions where they zip past the planets and continue out into space. So I want to plot 5 trajectories of those missions. These are the 5 fastest spacecrafts that humans have built. These spacecraft are traveling fast enough away from our solar system, away from Earth, that they will escape the sun's gravity. So, I'm not looking too closely here, but we have basically, I want to see, Pioneers 10 and 11, Voyagers 1 and 2, and then the 5th trajectory here is the New Horizons spacecraft, the one that visited Pluto several years ago. Now, these 5 spacecraft, the fastest spacecraft we've ever built, 4 of them were launched back in the 70s, Pioneers 10 and 11, Voyagers 1 and 2. And then New Horizons was launched in the early aughts. But we're going to project these trajectories out to their current distance from the sun. So we're seeing how far these spacecraft have traveled. 4 of them launched back in the 70s, so traveling for nearly 50 years. You can see how far they've made it, and astonishingly, if we remember that the distance across our solar system is measured by the diameter of Neptune's orbit is about 8 light hours. You can see that none of these spacecraft have traveled as far as light travels in a single day, even though they've been making these voyages for decades. So again, the universe is vast, and although we've done a great job exploring our neighborhood, we have barely scratched the surface in terms of where we've actually visited in the solar system, let alone the universe. But again, thanks to our observations from telescopes and other instruments, we are able to put together a 3-dimensional map of our universe. So we're going to leave our sun behind and begin to get a different perspective on the universe around us. What we're doing now is we're actually brightening the sun so that it is at the same kind of brightness as the other stars, so that we're drawing all of the stars with a consistent kind of brightness. And we've traveled so far so fast, we've traveled maybe 10 light years or so, that now you can see some of these stars are kind of drifting positions. We're vastly exceeding the speed of light as we kind of orbit the sun in this sort of virtual universe that we're showing you. And that means that we can get a sort of 3-dimensional sense of what's around us. And we have accurate positions for thousands of stars in our local neighborhood. And before we get too far, it's worth noting that we actually have found that many of these stars actually have planets in orbit around them. So if we could put a circle around every one of the stars that has a planet in orbit around it, we would see that particularly the nearby universe has a lot of these objects. And these planets are easier to find close to home. So as we travel farther away from our parent star, the sun, farther from Earth, farther from our solar system, you'll notice that we'll see fewer and fewer of these markers indicating planets around other stars. But you'll notice here on the left that we do have quite a few off in this direction, and I'm going to rotate around to get a better look at that. The process of finding these planets is a challenge, and some techniques have been more successful than others in terms of finding planets, but they require different constraints, different tools to execute. So if we look at this kind of trail of stars off here, of star markers off here to the lower left, what we're actually seeing is this kind of looks like a cone of these markers indicating stars with planets in orbit around them. And the reason we see that is because the Kepler mission, which has discovered the vast majority of the planets that we've found around other stars, the Kepler mission stared at this part of the sky for many years and was able to tease out faint changes in the light output from the stars that we have been able to interpret as the shadows of planets passing between us and the parent stars. The circles, I'll note, are scaled by distance. So circles that are closer to us appear larger. Circles that are farther away that are smaller are farther away. And so you can kind of see those Kepler data are kind of off in the distance in this perspective that we have right now. So this is really inspiring because finding planets around other stars, of course, it's not exactly like Star Trek, or if you choose your favorite science fiction interplanetary franchise, but of course, planets are where we would hope to find life in the universe. And so if we think about the potential of life in the universe, these planets are kind of a starting point and where we would think about looking. We haven't found a planet exactly like Earth. In fact, many of these worlds are very, very different from Earth. But as we continue our search, we are optimistic that we will someday soon find Earth-like planets, or perhaps it's better to say we might even be able to detect signs of life on other worlds. That's a fascinating topic in its own right, and in fact, our current show, Living Worlds, is a great place to begin thinking about that. But for our purposes, I'd just like to turn the question around a little bit. So if we look at this collection of thousands of stars with planets in orbit around them, we can also think about the way we have searched for intelligent life in the universe over the past several decades. And the way we've done it is to look for radio signals. Now, part of that is because we started that search when Earth was broadcasting a lot of radio signals carrying television, used for radar, radio signals actually emitted during atomic bomb blasts. Earth is probably going to become more and more quiet, less noisy in terms of radio signals, but it's a way to think about looking for life, looking for intelligent life around planets, around other stars. And so if we think about where we have broadcast, the volume of space we have filled with our radio signals, not completely, but at least partly filled with our radio signals, we can imagine a sphere centered on the sun. And that sphere we affectionately call the radiosphere. And it's about 80 some odd light years in radius. So about 80 years ago, Earth became radio bright. We began emitting a lot of radio signals. And those were strong enough to escape Earth's ionosphere. Not all, like AM radio really isn't strong enough to do that, but television carrier waves, those aforementioned radio bursts from atomic explosions, and radar are all strong enough to escape Earth's ionosphere. So you can imagine that if you were an intelligent radio astronomer around a planet inside this sphere, you could point your telescope back at Earth and maybe detect a signal that wasn't naturally occurring, but was created by a life form, namely us. So you can imagine this is sort of our footprint, our three-dimensional footprint in the universe around us. If those spacecraft that I showed you, the 5 fastest spacecraft we've ever built, are our nuts and bolts imprint on the universe around us, this is kind of our electromagnetic footprint in the universe around us. Of course, the bad news is that even if you were an intelligent radio signal around a radio astronomer on a planet around one of these stars, even if you pointed your telescope back at Earth, you wouldn't detect anything because our light simply hasn't had enough time to reach you. So radio waves traveling at the speed of light have traversed dozens of light years on volume represented here, but they haven't been able to reach all of the stars that we know to have planets in orbit around them. So it's a tantalizing thought to consider what it means for our search for life elsewhere, because if other civilizations are our age or younger, then their potential radiospheres would be even smaller, and they would therefore be harder, if not for us, impossible to detect. We have a little bit of an error here. I'll just acknowledge these two kind of images that appear to be floating behind our galaxy are actually the Large and Small Magellanic Clouds, which we'll see in a three-dimensional context now. But what I wanted to point out is that we are now bringing into view the entire Milky Way galaxy. So this beautiful spiral galaxy, of course, we haven't sent astronauts out to observe our Milky Way, so we only have calculated models of what it would look like. But the diameter of our Milky Way galaxy is about 100,000 light years. So if you think about it, we started by using our light travel time to measure a distance of just 1.5 seconds from Earth to the Moon, 8.5 minutes from the Sun to Earth, 8 light hours across our solar system, 4 light years to the nearest star, and yet now we're talking about hundreds of thousands of years, and in the case of our galaxy, about 100,000 light years across. And if you think about it, that's kind of close to the age of our species, or at least the time when our species left Africa, was maybe around 100,000 years ago, give or take. And for comparison, you can see our little radiosphere there, just a few pixels in the center of the screen, representing, again, our footprint in the universe around us. So this collection of hundreds of billions of stars, about 100,000 light years across, is our sort of city of stars in space. And just one last kind of cosmic measurement here, our distance from the Earth to the center of the galaxy is about 35,000 light years, give or take. And if you think about what humans were doing 35,000 years ago, well, we were painting the insides of caves. So we're rapidly getting to a point where these numbers and light travel time, which we selected as kind of a succinct way to measure large distances, rapidly becomes quite mind-boggling. Now, as I've been talking about the Milky Way, I mentioned the Large and Small Magellanic Clouds. These are two satellite galaxies. They're actually essentially orbiting our Milky Way galaxy. And you can see lots of other circles and points in the distance. Those are actually markers that indicate the location of other galaxies that we've measured distances to. So as we pull away from our Milky Way galaxy and the Large and Small Magellanic Cloud kind of accompanying us, we'll also see some dots sort of traveling with us. This is the local group of galaxies, a few dozen galaxies that are all kind of in this same part of space. But in fact, we are not in a particularly dense or populated part of intergalactic space. Instead, our local group is kind of a small town in the scheme of things. The big cities are seen here in these kind of clumps and clusters of galaxies. And of course, it's a very interesting thing in itself that galaxies are not just uniformly distributed in three-dimensional space. Instead, they do clump and cluster together. That's a great question in modern cosmology, the study of the origin and history of the universe. But we'll kind of get a hint at why we see this clustering of galaxies as we proceed through the program. One of the largest clusters nearby is the Virgo cluster. This giant clump of points is about 65 million light years from our own Milky Way. And again, if you want to think in terms of what was happening on Earth 65 million years ago, well, of course, the dinosaurs were just dying off. So when light left galaxies in the Virgo cluster to be detected by our telescopes here on Earth, dinosaurs were just having their last gasp here on Earth. We've now traveled so far from home that we're beginning to see, again, more dots representing individual galaxies. And you start to see that there are some interesting aspects to the data that we're showing you. Most importantly, it's, again, you can see this clumping and clustering of galaxies, but you'll notice there are many galaxies down here in the lower left or up here in the upper right. And it's not because there are no galaxies there, it's because we simply haven't finished surveying the entire universe. And it's a little challenging to come up with the distances to all these galaxies and measure the distances to these galaxies. So we're continuing to update this model with more and more data as we discover the distances and measure the distances to more and more galaxies. So it's not that there are no galaxies here, it's that we just haven't finished making our three-dimensional map. There's another artifact that I just want to mention, and by artifact I mean kind of a falseness to the data, which is you can see these kind of lines stretching back toward the center of our image, which of course is us here on Earth. And those structures are not real in the sense that the galaxies aren't really strung out along these lines. Instead, the galaxies are clustered like the ones that we saw close to home. But because of the way we make the measurements, there's an error in the distances that we measure, and the galaxies end up appearing in our model to be stretched out. So it's a little bit like the seams that we saw in the map of Earth's clouds, which are an artifact of the real data that we're using. This stretchiness and kind of looking like fingers pointing back to us here in the middle of the data set, those are an artificial aspect of the way we're rendering, of the way that the distances are measured. Well, I want to now pull far enough away to kind of hit the real punchline here. And that is that as I've been using this idea of light travel time as a way of measuring distance, there's built into that the realization that looking out into space is looking back in time. Whether that's a second and a half when you look at the moon, or 8.5 minutes for light from the sun to reach us, or looking across our solar system, light taking 8 hours, those distances mean, and because light travels at a finite speed, a fast one, but a finite one, it means that looking out into space is looking back in time. And so when we look far enough out, and because our universe seems to have gotten its start about 13.8 billion years ago, we're actually seeing some of the oldest light in the universe. And that's what's represented by this kind of modeled image that appears kind of as a backdrop to all of our galaxy locations here. And that's not really an image like the image of the clouds, or an image that of a galaxy that you might look at. Instead, this is it's actually almost literally a heat map. We're measuring the density and temperature of the early universe. The bright blotches correspond to hotter parts of the universe. The dark areas correspond to cooler regions. And we make this measurement in very long wavelengths of light, wavelengths that have been stretched out by the expansion of our universe. But it allows us to peer back to an early point in the history of the universe, when the universe was only a few 100,000 years old, compared to its 13.8 billion year current age. This oldest light in the universe shows us something really interesting, because the hot parts, the bright ones, and the dark parts, the cool parts, correspond to variations in density as well. The bright, hot regions are a little less dense than the dark regions, and the dark regions are a little more dense. So if you think about those clusters and clumps of galaxies that we saw close to home, this is where they come from. This variation in the temperature and density of the early universe over time evolved into the clumps and clusters of galaxies that we see close to home. And what's really amazing about this is an extremely high contrast image. So the bright parts are only about 1 part in 100,000 times warmer than the dark parts. So these are very tiny fluctuations in the temperature and density of the early universe. And yet, pulled together by gravity, and as it turns out, a very important ingredient of dark matter, we form the structures that we see nearby, clusters of galaxies, galaxies themselves. So this is the really big picture, and before I take us home, I just want to mention one thing that I've already kind of pointed out, which is we are here at the center of this three-dimensional model of the universe. And it's not because we are actually at the center of the universe, but rather that we're the ones drawing the picture. And because of that, because we're the ones who are plotting the distance of all of these objects from our vantage point on Earth, we're plotting them in space and time, because again, we're measuring their distance, but looking out into space is looking back in time. So this three-dimensional map of space-time has us at the center, because we're the ones making the observations in the here and the now. So with that thought, let me go ahead and pull in back toward our scattering of points that represent these amazing giant surveys of galaxies through the clumps and clusters of galaxies that we see in these surveys and close to home, back in toward our own Milky Way galaxy, our home galaxy, that galaxy of hundreds of billions of stars, about 100,000 light years across. I still have that little dot, which is actually a giant sphere that represents our radiosphere, our electromagnetic footprint in space, as well as all of those nearby extrasolar planets. For simplicity, let me go ahead and turn off the exoplanets and also our radiosphere. As we continue our voyage back to home, back toward the sun, we approach our solar system, we'll see the orbits of the 8 planets around our sun, and we'll head into the third rock from the sun, our own home planet Earth, back where we started our program, and of course, where you are listening to this live stream from. So I want to thank you for being such a great audience. I really appreciate taking the time to take you from International Space Station out to the edge of the observable universe. Didn't see any questions in chat, but we'll go ahead, and if we do see any pop up, we'll be happy to answer them. And thanks very much for taking part in our tour of the universe today. I hope you have a great evening.